Okay, so before we do anything, we have to start with our free body diagram, okay? And so, do you think this one is on an incline or not? Okay, number one I already told you, but can you tell from reading the problem that it's not on an incline? Okay, what's the clue in here that tells you it's not on an incline? Yeah, horizontal sidewalk. Okay, so this angle right here is just telling us that we're applying an upward force at that angle. So our object is horizontal, so it still has gravity and the normal force. Okay, it says we're applying a force at a 45-degree angle. So that's where that 45 degrees comes in. Are those the only forces I need on my diagram? I need friction also. So how do you know that I'm going to have a friction force? That's right. That's right. Anytime it gives us the coefficient or asks for the coefficient, you have to understand that that's giving us a clue that we have a frictional force. Okay. So here's our force of friction. Okay, so let's talk about a couple other things here. If it tells us that it weighs 400 newtons, what is that telling us? What variable is that? Gravity. Good. My force due to gravity is 400. So do I need to take that times 9.8? No. Remember, when it's already in newtons, that means they've taken it times 9.8 for us. Okay, so my FG is already 400 newtons. So anytime it's in newtons, that means it's already a force. Okay, so some people still are tripping up on that just a little bit. So whenever it's given in newtons already, it's already a force. Okay, if a force of 150 newtons is applied to the rope, so where does that go in my diagram here? On the hypotenuse, good. 150 newtons. Okay, and that means I would call this side F applied Y and F applied X. Okay, are we going to need to solve for both of those sides of our triangle? Okay, how many of you think, no, not so much? We only need to solve for the X. Okay, how many of you think, yes, we need to solve for both of them? Okay, the reason we do have to solve for both of them is because the normal force in this case is not exactly equal to our gravitational force. Remember, we're pulling up on that box, so we're taking some of the pressure off the normal force, right? It doesn't have to work quite as hard. So the reason that we need to solve for the normal force at all is because eventually we're going to use a frictional force, and the frictional force is the coefficient times the normal. Okay, so whenever we have friction, we're going to have to solve for the horizontal and the vertical. Okay, so just kind of remember that a little bit. Okay, so let's go ahead and solve for F applied X and F applied Y. So for F applied X, I'm going to use cosine and really, since it's a 45-degree angle, I only need to solve it one time. Okay, so I took 150 times cosine of 45. Are we all on the same page there? Is that not what you got?
I was wrong.
Okay.
My calculator is way off.
Is your calculator in radians instead of degrees?
I'm not sure.
Okay, the way you can check that is to hit mode right here. And if degrees should be darkened, it's like the third one down.
Okay, yeah.
Was radians darkened?
Yeah.
Okay, that's why. So degrees should be dark. Okay, so we got about 106.1 for each of those sides, right? So now we're going to look at finding our coefficient of friction. Before we can do that, we need to solve for our normal force. Would you agree? Okay, since our normal force has to go into our coefficient or our frictional force equation, we have to solve for normal force first. So I'm going to start solving now for my normal force, which is in the y direction. Okay, so how many forces do we have acting vertically?
2, 3.
1, 2, 3. Right, we have to use all three of those forces. Okay, remember, because we're pulling upward on that box, the normal force doesn't have to work quite as hard. Yeah, Courtney, do you have a question or no?
Oh, no.
Okay. What's our net force in the vertical direction? Do you know? Yeah, it's 0. Okay, so let's set up our net force equation. Tell me why again that it's 0. Yes, but we know from our problem that it's 0 because it's only being slid on our horizontal sidewalk. It's not moving vertically, which is why our net force is 0. So we're going to do upward forces minus downward forces. Okay, upward minus downward. Hopefully this is very much kind of ingrained in you by this point, right? When you set up your net force equation, you're always going to do upward forces minus downward. The normal force is what we're solving for. F applied Y we know is 106.1, and our gravitational force we know is 400. So I'm going to add that to the other side, and I'll get a normal force equal to 293.9. Okay, would you agree? Okay, and it's less than, right, if it would just offset gravity, then it would be 400, and it's less than 400 because we're lifting up on that box. We're making the normal force work a little bit less. Okay, now let's go in the x direction. Do we have any questions so far? Okay, in the x direction, how many forces do I have acting? 1, 2. Just 2. Okay, our applied x and our friction. Okay, what does it tell us in here when it says we're moving at constant speed? Good, the F net is 0. Okay, so when we set up our equation, positives minus negatives, we know that our net force is 0 because it's moving at constant speed. Okay, so our F applied x we know is 106.1. And our frictional force, we don't know our frictional force yet, but we know we can substitute this equation in for our frictional force. So we'll take the coefficient, which is what we're solving for, times our normal force. And I get a coefficient equal to about 0.361.
So you don't have to distribute the negative?
Now what I did was I subtracted this over first. Oh, you're right. I need to divide by the negative. You're right. That's my fault. So what I did was I divided by negative 293, and that left me with a positive coefficient. Does that make more sense? Yeah, your coefficient should always come out positive. Okay, so if that happens, that means we probably just forgot to do that. So that was my fault. Okay. Your coefficient should, for the most part, come out less than 1, right? Around 1 or less than 1. So if we're getting a coefficient of 15, right, something probably went wrong. So just pay attention to that. Coefficients also have no unit. So this is the one thing that we have that doesn't have a unit. Okay? Really similar to the one we just did. Okay, so on this problem, several of you still tried to do F net as 0 for your x, or your net horizontal force. But the reason we can't have a 0 net force is because it's accelerating. It's not accelerating very much, so it doesn't change our coefficient very much, but it does change it. So you take that 0.12 meters per second acceleration times your mass. Okay, and we solve for the mass by taking 137 newtons divided by 9.8. Okay, we should have gotten around 0.21. Okay, so this problem asks us to do something a little bit extra. And you kind of had to do this on one of your homework problems. But it tells us the plane, which is this right here, is 6 meters long and that it's 3 meters tall. Okay, so before we can do anything, we need to know the angle that the incline has been raised, right? We have to know the angle of the incline. So we need to find this angle of our triangle. Right? So if we have the hypotenuse side, and what's this one? Not to this angle? Opposite. Okay, so we have the hypotenuse side and the opposite side. How could we go about solving for this angle? Which one do we use? The second side. You're right. Sorry, I had to think for a second. Second side. So anytime we want to find the angle, we have to use that second button. So we go second sine of opposite over hypotenuse, and that tells us it's a 30-degree angle. Okay, does that make sense? Why we had to do that? We have to have this angle, otherwise we can't solve our gravity triangle, right? Because this angle fits right in when we start looking at our gravity triangle.
26.4.
Okay. Okay. We have a normal force. And what other force do we have acting?
Parallel.
Yeah, good. Parallel and good. So this is also called our normal force, and this is called our parallel force. And then we also have friction. How do we know friction is acting? That's right. It asks us for the coefficient, right? So if it asks us for the coefficient, we have to know that there's a frictional force acting. Okay, and so this angle right here, let me point it out a little bit clearer. This angle right here is going to be 30 degrees. Right? This angle between our origin and our gravity triangle is the same angle as the one of the incline touching the floor. So that angle right here is also going to be 30 degrees. So I'm going to just kind of pencil it in there. Okay? So our overall goal is to solve for the coefficient of friction. Are we going to need both sides of our gravity triangle, both parallel and the normal? Yes, right? Because in this problem, these two are going to be equal to each other. Okay, so if we solve our gravity triangle, we're going to solve for the normal force and for the parallel force. Okay, what do we know about Fg for this problem? What do we know about our force due to gravity? Good, it's already 1250. They gave it to us. Okay, I'll put these in a different color. So that's our hypotenuse right there. Okay, so to solve for the normal force, we'll take 1250 times cosine of 30. And for the parallel, we'll take 1250 times sine of 30. Okay, so if I start looking in the horizontal direction, I would say F net equals, what's my positive horizontal force? What's, that's right, what's the one that's pulling me downward on the incline? Yeah, gravity, but more specifically my parallel force. Right, the parallel is the horizontal component that's pulling me downward. So friction's my negative, so I'll say parallel minus friction. Okay, and since it tells us it's moving at constant speed, what's that mean for our net force?
0.
It's 0. Good. Okay, what can we substitute here for our frictional force?
U times
Good, the coefficient times
norm.
the normal.
Wait, 5, 8.
Good.